Okay, so we're going to look at some application problems. These are called logistic growth and decay problems. Alright, so the first thing we're going to look back at is exponential growth and decay. So this is from Math 1 and Math 3, but you may not remember it because it's been a while. So exponential growth occurs when a quantity exponentially increases over time. So an exponential growth function looks like this. Okay, where A is the initial amount, R is the growth or decay rate as a decimal, very important. Usually it gives you as a percentage, you're going to change it to a decimal. And T is the length of time. So let's color code that because I think that helps people. So A is the initial amount, R is the growth rate or decay rate as a decimal, and T is the length of time. Exponential decay occurs when a quantity exponentially decreases over time. So here's what that formula looks like. So you'll notice the only difference is that growth is going to have a plus sign and decay has a minus sign. A still stands for the initial amount. R is still the growth rate or decay rate as a decimal, and T is time. So let's look at two examples. Alright, so Brooke started her career with an annual salary of $32,000. That's your starting amount, so that's going to be A. Each year thereafter, her salary increased by 2.5%. Remember, that is a percentage. We're going to change that to a decimal. Write and use an exponential growth function to find her salary when she retires after 30 years. So our time is 30 years. Alright. So we started with 32,000. 1 plus, when we change 2.5% to a decimal, remember this is when you move the decimal place twice. So it's actually going to be 0.025. And we're talking about 30 years. So 30 is an exponent. So if I put all of that in my calculator, I get 67,122.16. That is how much she has when she retires. Okay, but look at the next one. In 1995, a magazine had 14,000 subscribers. The number of subscribers increased by 40%. Write and use an exponential growth function to find the number of subscribers in 2016. So our time is between 1995 and 2016. So we'll just have to subtract, but pretty easy. Alright, so we started with 14,000 subscribers. We are doing exponential growth because that's what it says in the problem, so I still a plus sign. If I change 40 to a decimal, remember I move it twice, so that's 0.4. And if I do 2016 minus 1995, I get 21 years. So when I type that in my calculator, I get 16,398. Oh, no, that's a way bigger number. My bad. 16 million, blah, 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 blah. You can read. You're good. Okay. So let's do two more. So we're going to do exponential decay this time. Alright, Katie drank an energy drink or an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system decreases by 12%. Write and use an exponential decay function to find the amount of caffeine in her system after 8 hours. So the only thing that changes is we're going to start with 150. We're doing decreasing, so it's going to be minus. When I change it to a decimal, I get 0.12, and I'm talking about 8 hours. So that's not too bad. So when I put that calculator, I get 53.95, and that's in milligrams. Alright. So the half-life of mercury 197, that's just the name of it, is 3 days. Okay. Write and use an exponential decay function to find the amount of mercury-197 left from a 50-gram sample after 20 days. Okay. So these are a little bit different. I don't know if you remember this from Math 1, but we'll see. Okay, so we're starting with 50 milligrams. My rate, we're talking about half-life, so it's just 0.5. And when you do half-life, it's the amount of time divided by the half-life. Alright, so our time is actually 20. So we're going to put 20 divided by 3. And remember, divided by 3 because that's the amount of half-life. So every 3 days you go down half. Alright, so when I put this in my calculator, I get 0.49, and this is talking about grams. Alright, that's not too bad. Okay, so now let's look at continuous growth and decay. Sometimes a quantity is constantly increasing or decreasing at an exponential rate, and not just after each year, month, day, hour, etc. The formula to the right, which I don't have enough room, so it's going to go right here. So the formula below can be used to find the balance of the account in this case. So R is for positive growth models and negative for decay models. The only thing you need to know is A is your ending amount, P is your starting amount, E is the number E, so 2.7128, something like that. R is rate, change it to a decimal, T is time. Alright, so let's do 2 different problems. So a garbage dumpster started with 4 pounds. I'm going to do P in yellow. The amount of garbage increased continuously by 35%. So I'm going to do my rate in red, and I'm going to do time in blue. Find the amount of garbage in the dumpster after 2 weeks. Alright, so we started with 4 pounds. My rate is 35%, which makes it 0.35, and I'm talking about 2 weeks. So you have 2 things in the exponential, and they're being multiplied. So all you gotta do is write this in your calculator, and I get 537.16. Alright, so let's do this next one. The population of a town is declining at a continuous rate. So when we do our rate, we're going to do a negative rate because it's going down. That's the only difference. So my rate is 1.5%. If the current population is 16,000, find the population in 8 years. Alright, so I started with 16,000. I'm going to do a negative rate of 0.015, and I'm going to times that by 8 years. So I get 14,190 people. And that first one was in pounds, if you want to be completely accurate. Alright. Now let's look at this one. This one should be brand new. The ones that we did previously, we've done in previous math courses. They're on Haiku if you need to look them back up. But this one is brand new to Math 4, so yay for you. So, logistic growth. Sometimes a quantity exponentially increases, but then levels out, approaching a horizontal asymptote. This is called a logistic growth model. Alright, so it looks like this. It increases really quickly, but then it's kind of going to level out. It's going to level out because there's an asymptote. So the logistic growth function is given as this. Alright. And now we're just going to use this to solve some problems. So a disease begins to spread in a town of 20,000 people. After T days, the number of people who have been infected by this disease is modeled by the function below. So it's really nice that they just give you the function. Using the function, find the number of people infected after 10 days. So all you have to do is replace t with 10. So I have 20,000 divided by 1 plus 1150 e to the power of negative 0.95 times 10. If you're doing this all together, remember to put that bottom in its own separate parentheses just to keep the calculator knowing what goes on the bottom. So you should get 12.19 billion. Yikes. No, wrong one. Sorry, I typed in the question for the answer for the second one already, and then I wrote that down. Let's try this. How about that? You'll never guess what the answer for the second one is. Just kidding, I already put it down. Okay, I'm embarrassed. So, the population P in millions of a country from 1850 to 2000 is modeled by the equation below, where T is the number of years since 1850. So, using the function, find the population of a country in 1920. So, if you do 120 minus 1850, that's 70 years you're talking about. So, really, all you're doing is this. Okay, and we're talking about 70 years. And now I put that answer that I put down the first time because I can't read. Alright, so this is what I got. Not too bad. Alright, so we're going to do application problems again in the next unit. And it's a little more challenging, but I think you'll be okay. Let me know if I can help you.